what I want to do today is to look at a little bit the principles of what is inside E325. What is inside Vampire? What is it doing? We will not look at very technical details, just the ideas, the architecture of the systems. But let's just try and remember what we spoke about on Monday. Remember this picture, huh? We said, right, if we have a world problem, we convert to a logic problem, we give it to the ATP, we get a logic solution, and you've seen that, the pretty trees and all that. And from that, we can extract a world solution. We didn't look too much at this. This area actually requires research more, but it's something. But then I said, well, how does this work? This is the normal way E or Vampire works. You take the axioms and the conjecture, you hand it into the tool. It says yes if it finds a proof. It says proof found, theorem. No, it says counter-satisfiable. That's the word, and sometimes timeout. But we know inside, these tools work by proof by contradiction. So we take the axioms and the negation of the conjecture, and we show contradiction, right? We show inconsistency, and that is yes. Or if we cannot, we show it's consistent, it's satisfiable is the word, then it's no or timeout. And the point I made, it's some along the line, is that if your axioms are inconsistent, then who cares? If this is inconsistent, it will say yes, inconsistency. And that's why for each problem, before we do the proof, we take the axioms and we check for consistency and try and check that. Sometimes it's not possible, but we try. And so that's why we have these. We take the axioms, we check yes, satisfiable, it's consistent, it's okay. Or it says no, then your axioms are bad. Then you have to do some work, then time out. So the point I want to just get back to is, remember, this is how the tools work. Take the axioms, negation conjecture, and look for contradiction. All right, so now, how do we do that? Let's just draw some pictures. So we'll start off at the top. We have the axioms, and we want to prove the conjecture. This is our wish. But we convert that to axioms union negation of the conjecture, and we want to show, let's just say here we want to show theorem. Here we want to show it's a contradiction, which in what we would say in the logic people would call it unsatisfiable. You cannot satisfy it. It is a contradiction. This is what's now happening inside. It's looking for unsatisfiable. Well, how is this done? Is to take this set and we apply a transformation. The transformation is called a satisfiability reserving transformation. Okay, so what does this mean, this sentence? It says, if this one is satisfiable, we produce something down here. Let me just call it S. If this is satisfiable, then that is satisfiable. Okay, so if there's no contradiction here, we apply a function, this function, and then this one has no contradiction. All right? Then we do it again. Doop, doop, doop. Okay. So we're going to have S, S prime, S prime prime, etc. We repeatedly do a transformation. And so what we know, if this one is satisfiable, it's no contradiction, then this one has no contradiction. If this one has no contradiction, then this one has no contradiction. If this one has no contradiction, is this one. And what we want to end up with is a set that contains false. And if that set contains false, that's definitely a contradiction. False is the opposite. So we would do these transformations until we get to a set that contains false. And now we know, and if this is false, what do we know? This is unsatisfiable. If you have false, it cannot be true. And so it's unsatisfiable. Well, if this is unsatisfiable, this was satisfiability preserving. And so then that one is unsatisfiable. That one is unsatisfiable. That one is unsatisfiable. And eventually, that one is unsatisfiable by the argument. So we preserve satisfiability forward. We show unsatisfiable. Then we can argue backwards, unsatisfiable. This one is unsatisfiable. Therefore, we have a theorem. So, you get it? You're good, yeah? You have to do translations. So what we have to look at a little bit now is what are these satisfiability preserving transformations? And inside E, inside vampire, there are two types of transformations. There's the first transformation is convert to clause normal form. All right, so what we can do is take the logic with and implies and not and everything, and we convert to a very simple form. Okay, I'll show you. Then the simple form is easy to do the reasoning. And then the second type of transformations we'll look at is called inference rules. And in particular, the inference rule I'll show you is an inference rule called resolution. And you know resolution probably. You know modus ponens. If A implies B, you know A, then B. Yeah. Okay, so that's resolution is a general form of modus ponens. It's, you know the rule. So let me take a shot about this, screenshot. So now what I want to do is today, just to begin, rather than doing full first order logic, full first order has for all exists, we just go back to propositional. Remember, the police are happy and things. We just propositional logic. So just to show the ideas, and then we can lift the ideas to the next logic. So let's go back to the examples. Propositional logic. Okay, we remember this? Okay, we saw this one on Tuesday. So this now has implies, it has or, implies, it has not. We're going to go to clause normal form. Let me tell you about clause normal form. Colors. We call it CNF. All right. This is something like L1 or L2 or L3 ... or Ln, where Li is an atom or not atom. Okay. So we have no implies, no anything else in clause normal form. But let's do an example so this becomes a little more concrete. So we take this, I'm going to go here and steal this example. Just copy it. Okay, so we're going to have the axioms are, let me just, it's this. Can I just be sure? Instead of horse races fixed, I put HRF, huh? Just to be quick. Bookies crooked, I just put VC. Okay, tourist trade declines, TTD, just for shorten. Huh? And so this one would be, this is TTD implies happy police HP. We have not happy police. And then the conjecture, C equals not HRF. Huh? That's our problem. So remember, what do we do first is we take the conjecture, we negate it. Let's just remind you what we have to do here. Let's bring up a tool for this. We're going to take the axioms and negation conjecture. Huh? So the first step we're going to have to do then is this. All right, so what we want really here is negation C, which is negation. Sorry. So now we have to convert to clause normal form. So let's take this second one just for an easy beginning. How do we make implies goes away? You know how to convert implication to disjunction? Yeah, what is it? This is, no, it's not TTP or HP, huh? Everyone knows this? Yeah, you know this rule. So what will this one be? It's negation of HRF or BC or TTD. But then we can do another step. How do we make this go away? De Morgan? Yeah, De Morgan law, right? Everybody knows De Morgan, I think, yeah? So this becomes not HRF and not BC or TTD. But we can do some more. We can now do distribution. So this will become, I have to just write it here. It's not HRF or TTD and not BC or TTD. Let me just, sorry, I ran out of space there. But you know that rule, huh? To distribution and over all. This is familiar territory. All right, but now what we look at, let's just see. This one, it looks like this. L1, it's negation atom, or L2 is HP. That's a clause. Here, that is one clause, and here, that is one clause. Okay? So what is not HP? This is already a clause. Not, we all know what to do, huh? So that's a clause. So the final set we have, I'll write it out. The set S that we show here, the first transformation is to convert to clause normal form. So this set S becomes, well, I have to make this go away. S is, not HRF or TTD, and not BC or TTD, not TTD or HP, negation HP, HRF. So now we can start doing, you can do it with modus ponens, but let's rather think of the idea of the resolution inference rule. So the general idea, something we know, if I have A implies A, wait, let me think. Yeah, A implies B, wrong way around, implies B, and I have B implies C. What can we produce out of the bottom of that is A implies C, huh? Everyone's happy with that rule. But now we can write this. How do we write this? This is not A or B, not B or C. And the conclusion down here is not A or C. Huh? So the resolution rule does this thing. It says, look in one clause for a positive thing is positive, and the same thing negative in the other clause. Cancel them out, then what is left is not A or C, not A or C. So resolution says in one clause you look for positive, the other clause you look for negative, cancel, and whatever's left is the result. So now we could take this. What can we do here? Let's see. We might say, let's do this one and this one, huh? It's possible. What's the result? Is we're cancelling not TT against positive. So this will give me not DC or HP, huh? All right. And what else could we do? There's lots of possibilities. Maybe I do this one against that one, huh? Because I can take H, not HP and HP. What do we get here is not TTD. And what else can we do? How about now? Which one? You want to do HRF against the top one, huh? Yeah, so hopefully my lines don't, so like that too. And we get TTD. Oops, let me just put that a little bit higher. Oh, now we can do this. TTD, not TTD. What do we get left over? Nothing. And when there's nothing left, that's false. Okay, so now we've gone down. We have done this inference of resolution, cancelling. That is satisfiability preserving, and we can prove that. It's easy proof. So we did in this proof, remember the pretty trees with the flashing lights? Well, here we are. Just put the computer, doesn't work. Okay, you know the idea. This is the bottom of the tree, and in the proof is this, we have that, we did that. These are the ones in the proof. That is the finished proof, the pretty tree. And this one over here, this was a waster. We did some work we didn't need to do. And that's theorem proving for you, is trying to find which ones to combine each time to do it so you don't do wasted work. That's the whole story, really. All right, so that's okay. So now we take a screenshot of this. Let's go back into this example, and everyone remembers this challenge, huh? So let me make it smaller over here. So what is this? We did, you can remember Q, what is it? Q, quiet, paz, I was or tranquilo, but we do it in English now. So it's quiet implies resting. Mm-hmm. Resting, peaceful and quiet. Mm-hmm. Peaceful, then you are quiet or resting. Peaceful implies to or are. Okay, so that's the axioms. Like this. And therefore, being peaceful is the same as being quiet. P, Q. Okay, everybody's got a piece of paper. Convert that to clause normal form on a piece of paper, or you can type it. But let's do the transformation. And if you need some help, if you don't know how to convert equivalents, then hi guys, then you can do it. But everyone can convert to clause normal form. Yeah, do the work. Pen, paper. Good. Work, 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 work. I don't believe you finished. It's too quick. It's quite a big one. You got it? Did you remember to negate C? Negation of C? Ah, 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 ah. One more minute, then we go through it together. Yero, you close? You finished? Yeah, not quite. You finished? Andrea, you finished? A little bit more work to do. All right, let's do it together, huh? Okay, so this first one is easy, huh? You got it? It's no Q or R, huh? The next one. Okay, this one is no R or P and Q, which then has to become is no R or P and no R or Q. Just so it fits together, huh? That's correct. Yeah, you're in charge. Next one is no P or Q or R. Finish immediately. Okay. Last one, step one, negate C. So we need to do negation of P equivalent to Q. Negate the conjecture. And now, how do we make this go away? It's the negation of P implies Q and Q implies P. So now we do De Morgan's rule. I'm going to just give myself some more space. So it'll be negation. Well, let's do De Morgan. Let's get rid of first, we get rid of the implication. How do we make that go away? Negation bracket, bracket, negation P or Q, and negation Q or P. That gets rid of the implications. Now we kill this guy, push him inwards. So we get negation of negation P or Q, or negation of negation Q or P. Is that about right? Yeah, I've got too many, don't need that first bracket now. Agreed, correct? Yes, and we're on the same page. Now we drive in the negations, again, push the negations in with De Morgan. So it's P, and negation Q, or negation Q, so it's Q and negation P. That's correct. This is like computer science 1, mathematics 1. Okay, and now we have to do distribution. So we get P, P or Q. I didn't put the bracket. P or Q, and however you like to do it. P or not P, and not Q or Q, and not Q or not P. Okay, so everybody did that. So let's just underline the clauses now. We have this one, we have this one, we have this one, and this one, and that one, that one, that one, that one. So there's 8, ocho, 8 clauses, huh? Right, so now we take a screenshot. Then we have to do, I'll write it out again for everybody. No Q or R, no R or P, no R or Q, no P or Q or R, P or Q, P, not P, not Q or Q, not Q or not P. All right, so now everybody can do the resolutions, keep canceling until you've got nothing left. Now you have to think, which one shall I do first? Many possibilities. Eh? Well, I'll give you one clue. Remember, you are trying to get to false at the end. And this is a tautology. And a tautology will never help you find false. So these two you can ignore because you will never get to false using a tautology. So now you have to decide which two. I give you all a few minutes to see if anybody can do the sequence. Yeah, you have to think. This is why E and vampire are very good, because they can decide what to do and what first. I'll give you a few minutes to try and see how much trouble. Then I'll show you some ideas on how you can do this efficiently. Try. Paper. I can give you a piece of paper. Draw pretty pictures. Okay. Did I do this correct? This is not on. Okay. Wow. I think I have a mistake. All right, it's quite difficult to find it, eh? Okay, I'll show you the answer because I know it. So what we can do is do this one with this one. We cancel not R with R. And what do we get left? P, whoop, put my cursor a bit higher. P, no, that's not going to work. Sorry, I have to think. No, we must do not that. That's not good. What's your suggestion? I think this one will work. These two. This is a good idea. Not R against R. What do we get left? Is Q or, we've cancelled not R, Q or not P. Or not P or Q. Yeah, but we know Q or Q is just Q. And so we can do a simplification here and just delete that. Huh? Then what can we do next? Any suggestions? Was it a P? Huh? P or Q? Yeah, but then we can only cancel one. We cannot cancel both. We can do P with not P. Yeah, but if I do these two, you see this? What do we cancel? P with not P? And what are you left over with? Q, whoop. Yeah, Q or not Q. It's a tautology. It's no use. So that's not a good idea. Any suggestions? I don't know what the answer is. I made a mistake in my notes. What? The last, this one and that top one. This one. So that and that. Ah, that's a good idea. Good thinking. That's why you were the dean. So we do those two. We're cancelling not Q against not Q. What do we get left over? Negation P or negation P. But two negation P's, we just kill one of them. It's the same thing. We know that P or P is the same as P. Ah, now we're getting somewhere. Now what can we do with this? Maybe these two? Not P against P, we get here not R. What else can we do? We can do these two together. Maybe these two. R, not R and R. We get not Q. All right. And now I see the answer. We can do this one and this one, not P and P. We get left here Q. And then final step, not Q and Q. And we finish. False. Let me just move this along a bit. So that's quite difficult to do. And let's look at which were the good ones. This is important. This is good. So therefore that's good. Therefore that's good. Therefore that's good. Therefore that's good. And therefore that's good. And therefore that's good. And therefore that's good. Oh, we didn't waste too much time. Yeah, only the one bad one at the bottom produced a tautology, which is never going to help you. All right, so now we have to find an efficient algorithm for doing this, because otherwise you sit there and... So now I'm going to show you a very common algorithm that is implemented, and it was developed at the Argonne National Laboratory. It's a research laboratory near Chicago, Argonne National Laboratory. And so this, because of the name of the laboratory, it's often called the ANL loop, Argonne National Laboratory loop. Other people will call it the given clause loop. All right, so here's the algorithm. I just have to type it out. Give me some time to type it. You have two sets. You have a list and a set. List to be used. I'll just call it TBU. And a set can be used. We call it CBU. So the to be used is a list. It's ordered. It's a priority queue. And can be used is just a set, a random set like that. Then we initialize the set like this. We say to be used equals CNF of axioms, union, negation of the conjecture. So we do what you just did now. We convert to clause normal form, and we put it in the to be used. Now, the to be used is a priority queue. Everybody knows priority queues. You're teaching it right now. Okay. And so the order of that priority queue is the critical intelligent part inside E and vampire. How do you order that priority queue? And we'll have some ideas. What is a good ordering on the priority queue? Initially, we set the can be used with the empty set. All right. Then we say while loop, while false, not in CBU. Now we did in Python style. Okay. Select given clause GC from CBU. You take it from the front of the priority queue. You take one off this queue, and I'll draw you a picture to make this all clear. Let me finish typing it. To resolution between GC and others in CBU. This. Okay. Put inferred into to be used. So that's the entire algorithm that is inside E with some extra pieces, but this is the basic idea. You can think of it being like this. You have, this is the can be used. and we have the priority queue. The to be used. And we initialize the to be used with the clauses. Okay, so we have here, this is the priority queue with the clauses that we had. The last one, we had 8 clauses. And you have to decide which order to put them in here, etc., etc. Then you take one from the bin. We look, is false inside here? No. So we take the front one from here and we move them into here. We take, select one, let me just draw that again. Select one there from move it in. And now we say, do resolution, the cancelling rule, between this one and anything else that's in here. Well, now there's nothing else. So nothing, no resolution, nothing is inferred. Go around the while loop. Then we get another one. We bring another next guy in. Okay. Like that. And maybe, again, maybe nothing happens because it depends whether it is possible between these two. Is there some way to cancel? Maybe there's no way to cancel. Maybe nothing happens. So now we do another one. We just imagine. And now maybe this time we can do like we did in the last picture. We can do that one. So this now, this is the current guy. Huh? We can do that one and that one. And we can do that one and that one. And what we produce, 2 new pieces. Then we take the 2 new pieces. Put the new guys in there. This is put the inferred into the to be used. And we go around the loop. Over and over, over. Until at some point we have false. Okay, we can even be a little bit far. Well, false, we can even be, if we want to be a little bit smarter. Let's just do this. Depends some other thing. But we could just look. So when you have found false, you put false in here, then you stop. Now you have finished false. So the secret is, how do we keep this in order? What order should we put these in here? Well, remember what you're looking for. Eventually, you want to take something like P, not P, and cancel, so you have false. So you want to take a small thing and cancel it against a small thing. Take 2 small things and cancel them, you get false. If you take 2 big things and you cancel, you never get false. Because you must have P and not P, or R, not R, 2 small things to cancel. So a very simple ordering here is to put the smallest things at the front of the queue. Poquito at the front, El Grande at the back. Yeah. And this is sort of like what you see. Because if you take 2 big things and you join them, you get 1 big thing. You know that? You have a fat father, fat papa, fat mommy, fat baby. No good. We want skinny father, skinny mama. And we go cancel them out. So now we can try and do that with the example with the horse races are fixed. How should we do this? Yeah. I have how much memory you have in your computer. So it's a good question, because about 10 years ago or 15 years ago, computer memory got very cheap. I don't know if people remember, maybe you didn't have it when you were young, but you guys remember, suddenly memory in a computer just got cheap and big. And so the engineers made theorem proving much better because people had much more memory. Yeah, it's a reality that we had to hit up against. Okay, so now I have to get the example. Sure. That's different things. So then this is the simplest version. Vampire, he has the red pathway coming in. He has like 8 of them, different priority queue. And he says, I use this queue a bit, then I use this queue a bit, then I use this queue. And then, or if he has octa-core or quad-core computer, he runs them in parallel. Yeah, so he has different priority queues running in parallel or concurrently, depending on what computer you compile for. Yeah. I mean, so that's part of technical programming inside E. E does the same thing. Vampire is technical programming. You need to know about threads or parallelism and synchronization of data structure. So the inside it is quite complicated computer science. All right, so now I have to try and think how I'm going to draw this. Okay, so here's our can be used. And we're going to put into the pathway the example from the horse races are fixed. And if you remember, there was, I'll get up the picture so you can see it. Yep. So here is the clauses. So what we would like to do is put at the front of the priority queue, these two, because they are smaller. And then we put those guys at the end of the next. And they are all the same. They're all of size 2. These guys, size 1, size 1. All right, so we're going to have in this queue, at the front of the queue is tilde HP. And then behind him is horse HRF. Hold on. I do it a different way. I'll write the queue backwards. Okay. Tilde HRF or GTD. Tilde BC or GTD. Tilde GTD or HP. Tilde HP HRF. So this is my pipe coming in, huh? So we start off, which is the first one? We take this guy, HRF, we take him off the queue, and we bring him in here. And then we say, HRF, anything else here? Nothing to do. All right, so next we go to, not HP. We take him off the queue, put him in here. Not HP, nope, no possibility. All right, so now we take not TTD HP. What can we produce? We can go this one against this one, huh? We can cancel, we can do resolution. Him against him. What do we get? No TTD, huh? And then we have to take this guy and we put it here. But where do we put him? At the front, huh? Because he's size 1. So he comes up over here. I'll just put him there. No TTD. You see it? All right, Good. Right, now we go again. We go around the while loop. It's just a while loop. Nothing pretty big here. So what do we have to take? No TTD. We take him out of here. No TTD. Now, what can we do? No TTD with this? No, no TTD with this? No, no TTD? No, nothing to do. All right, so we have to go to this one over here. No BC TTD. That's it. No BC or D. Right, what can we do? We can do this new one. Here's the given clause against that guy. So we can play that, these two. So we go him against him. And what is left over is no BC, huh? And anything else? No other possibilities, only one possibility. So now we take this guy. You know the game now. You can imagine how to play this. We move him up here. So he is size 1. So he must come to the front somewhere here. No BC. Go around the loop. Same again. All right, so now I try and go a bit quicker, as fast as I can draw. No BC. He comes out of there. And he comes into here. No BC. No BC. No, nothing. Nothing to do. Last one. And we didn't. Is this guy. No HRF TTD. HRF TTD. What can we do? What are the possibilities? The two at least. How about these two? Okay, so we can do that one with that one. Yeah, and we get TTD. But what else can we do? We can also do that one with that one. Is that the guy we just, yep, yeah. This is the chosen clause. This, we have to use the one we just brought. And those two together produce no HRF. Okay, what else? Nothing else? That's it. So we grab these two. And they have to go up to here. They're both of size 1. What can we do? We can put them in any order. Which we just even PTD and no HRF. All right. And now we can see it's going to finish immediately now, because when I take the first one, no HRF, and I bring him into here, no HRF, immediately then we can do and we get false. And then we put, formally in the algorithm in computer science, then this guy, we grab him, sorry, wrong color, wrong shape, and we bring him to here, and then we can finish the while loop and we're done. So that's all what's happening. This is the basic idea. There's some extra modifications that you make it. I started doing it without doing the ordering last night. Just without making the smallest one at the front, I just did the order. I wrote it down, and then I got bored. That was it. So it didn't work. So then I thought, okay, we have to do the order. Are we going for time? 5 o'clock. Okay. So let's just look at a few ideas that can make this more efficient. In this example here, we generated, at some point we had this not HRF or TTD, and later we produced just not HRF. Huh? So consider the relationship between those two. Which is better information? This is more information because, you know, definitely no horse race is fixed. Definite information. This one, no horse race is fixed. All tourist trade declines. You're not sure. So this is stronger information. And also, so that's one way to think of it from an information perspective. This is stronger information. But imagine what we want to do to finish. How did we finish? We took not HRF against HRF to get false. But if I had done, but here, if I do HRF against not HRF, I don't get false. So this one is stronger to produce false. And this is a rule called subsumption. All right, I'll write it here so you can see the word. All right, this is a rule inside every theorem prover. It says, if you produce something like not HRF, then we delete that one. So if you produce good information, you delete the weak information. You keep only the strong information. See, so for example, so as you see here, that one allowed us to delete that one over there. And for example, here, when we saw that, that would allow us to delete that one. Because no TTD is better information than the OR. And I don't think if there's any other cases. Yeah. So this happens, and in the algorithm, let's take a screenshot of this. No, not that one. What happens is, in this point over here, at that line over here, inside here, you do that checking. You produce some new things, okay? You produce some new things. Then you say, now I have new things. Are some of these new things very bad? They're very weak. They are weaker than something you already know. Delete those new things. Don't keep new things that are bad. I'll just wait for the translation. Yeah, and then, so now you have some good new things. Now you look if the remaining new things are better than something else you know. Delete old things that are weak. So that's the forward and backward subsumption. Okay. So now I've shown all of this to you in terms of propositional logic. What's the story with first order logic? Propositional logic, we started off with this idea. We convert to clause normal form. Easy propositional logic. You can do it, Boolean algebra. And we did resolution. But now when you come to first order logic, it's more complicated because you have variables and you have for all and you have there exists. So that complicates the situation. Let's just look at some simple examples in first order logic. So I'll write something. I'll write it in TPTP syntax. For all students, for all children, there exists a parent such that loves parent-child. So I'm trying to say, for every child, one parent loves the child. Okay? That's a very sort of normal sort of thing. Now, what we have to do is, how do you get rid of this existential quantifier? And so it's a process called scholemization. So what this would be converted to, and I don't want to show you, you would produce loves SKC, comma, C. And that's a statement for all C. That's how you get, this makes it now, in first order, you've removed the existential quantifier. It means that all the variables that are left, in this example, there's the variable C, it is universal. So you can remove the existentially quantified variables with this trick called scholemization. It's called scholemization. It's named after a Swedish logician called Thoralf Skolem. So what does this mean? Let's think of this in terms of your family. For every child, at least one parent loves the child. Maybe only one, maybe two, but at least one parent loves the child. So this is a new function that has been invented in the process. This is the function that when you apply it to the child, it tells you which parent does the loving. So it's an imaginary function. It says, if I give you this child, I apply the function, it will point to one parent who loves you. So that's part of the trick in the conversion to clause normal form and first order logic. The rest of it's the same as propositional, but you have to remove the universal, the existentially quantified variables with this trick. So that's one thing. The next thing is resolution. Let me give you an example. P of X, X, or Q of F of X is one clause. And here's another clause. No P of A or R of B. So now, can we do the cancelling rule here? It's not exactly the opposite. You see here we have PX, not PA. So the cancel is not exact. All right. But this X is a variable. And we know after this that we have got rid of the existential variables. All variables are universal. So this is for all X. Yeah. So if it is for all X, we know it's true for A. It's one possibility. We're saying for every X, so let's choose that one. And now, we can cancel those two. And what is the result? It's Q of F of A or R of B. Like that. So when you're dealing the resolution rule, when you're doing cancelling, you have to look, do I have to take a variable and give it a value when I'm doing it? All right. And that is called unification. This idea, I made this one look like that one by unification. This one is solemnization. All right. So that's the second thing. When you go from propositional to first order, you need to do this magic when you convert to clause normal form. You need to do this magic when you do resolution. One more. The ordering. We saw in our example. Let me go over here and pick it up. This one is it? We put the small ones at the front. With only one piece. Then we put the ones with two pieces, if three would be after that. So now, consider this situation. If I have P of X or not we can use the same example, not Q of f of x. I use the same example, and I want to compare that with not p of a or r of b. Are these two the same? Which one should come in the front of the priority queue? They both have two pieces, two. So what happens? The first step is you count symbols. Uno, dos, tres, cuatro, cinco. All right. So this one is 5. This one, uno, dos. This one is 4. So you put this one at the front. You count the symbols. This is very effective. But you can, now there's another thing. Let's imagine now we've got, I have another clause over here. No Q of Y. How much is this one? 2, huh? Now, what things, let's look what things we can do. We could do this guy can cancel against that guy. One possibility. This guy can cancel against that guy. That's what I showed you. That's what we did here. Another possibility. There are 2 possibilities. Which one should you do? Well, we know that this one will be at the front of the queue, but you can make another rule. It says, for each clause, you only use the literal, which is the symbol is at the best symbol. P, A, B, C, D, E, F, G, H, I, J, K, element of P, Q. All right. And so we say P is the one I have to use here. A, B, C, D, and then P, this is the one I have to use here. So what this will tell me, I cannot use Q. I have to use P because P is before Q. And so we have to do the blue one, azul. And then when we finished, then we can do later. So if we do the blue one over here, we get this result. It's Q of F of A or R of B. Okay. And in this one, which is the most important symbol? A, B, C, D, E, F, G, H, I, J, P, Q. Now I can do that one. So then I can do that. I can do those 2 together now. Not Q, Y. I change Y to FA because it's for all Y. So I can make them FA. And the result then would be R of B. Okay. So that's another way that you can reduce the number of possibilities. And so you reduce the amount of data that's being generated as you do this stuff. And in fact, there's a more, even rather than using A, B, C, D, E, F, G, there's a thing called, you might know the method Knuth, Bendix order, KBO, which is a very precise way of saying which piece of a clause you must work with. And so that was, people know Donald Knuth, computer scientists here, right? So he was one of the guys who invented this ordering idea. And that is inside E and vampire Knuth-Bendix ordering. And it is used very, very often for many things. So the implementation is very, very fast implementation of the function. It's a sorting function to sort, and it's very fast implementation with some clever work done by Bernd Luchner to work out the algorithm with clever data structures to make it very, very fast sorting because it gets called all the time. Okay. All right, only 2 more little ideas and then we'll stop. You've seen in the examples so far, you had things like teacher of Joe equals Jeff. Huh? We saw that. And we've seen something also like Bob not equal Maggie. Okay? So what we're focusing on here is equality. The examples I've given you, the equality was very simple. When you use theorem proving in mathematics or engineering or anything, equality is a lot of equality. And it means, and resolution, if you use resolution with equality, it goes crazy. It's not good. So rather than using resolution when you are dealing with equality in a reasoning, all of the theorem provers, Vampire and E, have a different rule called superposition. Yeah? And superposition, yeah. So you don't know resolution, you use superposition instead. And superposition deals with equality very efficiently, and it also uses KBO, by the way, it's inside that. So you get very efficient reasoning about equalities. If you think in mathematics, often a mathematics proof is something equal something, therefore something equals something, therefore something equals something. It's a sequence of equalities. If you do that with resolution, very slow. You do it with superposition, very fast. And then the last thing to finish today is we spoke about arithmetic. Okay, so we're talking about integers. If I could type rationals, maybe. Rationals are kind of funny things. And of course, we all love real numbers. In the world, numbers are everywhere. And so we have to deal with it. If you want to do this, and we discussed this yesterday, if you want to have this, you must use the TFF logic, at least. Plain first order logic is not strong enough for arithmetic. You need TFF logic. So in TPTP World, Vampire can do it, no E. He can't do it. He cannot do this work here. It's very specialized work. There's a whole community of people who study how to do reasoning with arithmetic, and this is the people called satisfiability modulo theories. These people, the SMT people, who are kind of my opposition in this research, they don't worry so much about efficient reasoning, superposition, blah, 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 ordering. We have problems with a lot of mathematics, and they have very special reasoning internally to reason about arithmetic. Reasoning about arithmetic is difficult, and so they specialize at that. All right, so that's all I want to talk about today, even we've gone for an hour and a half. So that's sort of the big picture of what's happening inside. And if you want to write your own theorem prover, it's possible. I mean, I've just finished teaching a course now in Miami, and the students use Prolog programming, and they implement their own theorem prover with many of these ideas. Okay, so it's doable. But to make high performance, if you're interested in doing it, I can just give you some hints. If you want to build your own, you can take a very simple one. It's called PyRes. You can Google PyRes. And it's in Python. So that's Python resolution. And it's a very simple one. And you can take it and it can solve some problems. And then you can modify the source code to make it better with more ideas. It's the same man who wrote E. He wrote this for teaching. So it's source code in Python, freely available to do this, to learn how to write your own theorem prover. Let's see if we can find it. PyRes prover, something like this. There you go. It's on GitHub. So the source code is there. You can run it immediately. It's not very strong. And then you can add things and play with it if you're ever interested in doing that. Or you want to have something special. You've got some good ideas. You can do it in Pyrace. Okay, so that is complete for today. Now, we have to ask the big question. Does people want more tomorrow? It's right. More? Yes. So tomorrow we can do some more strange logics. And now we can choose a time that is good for whoever's left. Carlos, can you coordinate a time? What will you say for tomorrow? So Fabian, can you guys put what time is good for everybody tomorrow? Yeah, I want to, so tomorrow I can teach some more of the strange logics and we do some more practice.
Universidad Nacional de Colombia, proyecto cultural, científico y colectivo de Nación.